In the early morning of a calm Pacific day, a metal cylinder roughly the size of a person is lifted over the railing of a research vessel and held for a moment above the water's surface. The device is dark, smooth cased, and precisely engineered, its pressure housing machined to withstand conditions it will not encounter for several hours yet. Then it is lowered, and the ocean takes it. The first few meters are bright. Sunlight penetrates surface water with enough force to illuminate the device as it descends, the casing catching the refracted light, scattering it in moving patterns across the hull of the ship above. The water here is warm relative to what waits below, and the light here is real, direct, visible in the way that light at the surface always is. The device passes through it quickly. By 10 meters, the quality of the light has already changed, the reds and oranges stripped away by the water column, leaving only the cooler end of the spectrum. By 30 meters, the light has become something thinner and more diffuse, less like sunlight and more like the memory of it. The device keeps descending. At 100 meters, the water around the hydrophone is a deep, even blue, not dark yet, but no longer bright. The temperature has dropped. The pressure, already several times what it was at the surface, presses evenly on every face of the instrument's casing, and the engineering that went into that casing is the reason the device does not register this as a problem. It is built precisely for this. It continues down. By 200 meters, the light is nearly gone. Not all at once. This is not a threshold that announces itself. It fades progressively, the blue deepening towards something that no longer has a name in ordinary language, and then the dark becomes total. The instrument passes through that transition without registering it, because the instrument measures pressure and acoustic energy, not light. The darkness means nothing to the machine, but the temperature continues to drop, and the water through which the hydrophone moves is now cold enough that warm-blooded animals would not long survive in it without protection. The device has been descending for several minutes now. Below it, the mooring line and anchor are already in place, set during an earlier deployment operation. The hydrophone is being lowered on a separate line, carefully toward a specific depth. Not the seafloor, not the surface, but a depth in between that the team aboard the vessel has been targeting with some precision. This depth is not chosen arbitrarily. It corresponds to a layer of the ocean that was understood by the time this deployment took place in 1991 as one of the most acoustically remarkable environments on Earth. Somewhere between 600 and 1200 meters depth, sound behaves differently than it does anywhere else in the ocean. The temperature of seawater affects the speed at which sound travels through it. Warmer water conducts sound faster. Colder water conducts it slower. Pressure has the opposite effect. Higher pressure increases sound velocity. As depth increases, these two competing factors interact in a specific way. Temperature drops sharply in the upper ocean, slowing sound velocity down. At greater depth, the temperature stabilizes and pressure becomes dominant, pushing velocity back up. The result is a minimum, a layer where sound velocity is at its lowest in the water column. This minimum is where the hydrophone is being aimed. Sound waves traveling through water refract, bending toward regions of lower velocity, the same way light bends through a lens. A sound wave moving downward through the upper ocean slows as it approaches the velocity minimum and bends back upward. A sound wave moving upward from below does the same, bending back down before it escapes. The result is that acoustic energy becomes trapped. It moves horizontally, bouncing between the upper and lower limits of this velocity minimum layer, but it cannot easily escape above or below. It propagates outward through this corridor, losing very little energy as it goes, traveling across distances that would be impossible for sound anywhere else in the medium. The hydrophone reaches its mooring depth, and the lowering line is released. The device settles. It is cold here, near 2 degrees Celsius, and completely dark, and the pressure acting on the instrument's outer casing is already many times greater than anything at the surface. The acoustic transducer inside the casing, a pressure-sensitive element that converts the mechanical energy of passing sound waves into electrical signals, is now positioned exactly within this corridor of slow sound. The first acoustic event it records that day is the low, continuous rumble of a distant ship, too far away to see, too far away to know the vessel is above. The rumble travels through the corridor and arrives at the transducer as a sustained electrical hum. The instrument logs it and keeps listening. The corridor the hydrophone is now moored within had been given a formal name by the time NOAA deployed this instrument. The name is the SOFAR channel, an acronym for sound fixing and ranging, derived from a wartime and early Cold War technique that used the layer's long-range propagation properties to help locate downed aircraft pilots who had dropped small explosive charges into the ocean. The channel's existence as an acoustic phenomenon had been understood theoretically since the mid-1940s, when oceanographers and physicists began working out the mathematics of how sound velocity varied with depth in seawater. Within a decade of that theoretical understanding, the technology existed to deploy instruments within it, and the acoustic properties of the channel had become a matter of considerable military interest. The United States Navy understood early on that a submarine traveling at the right depth would be difficult to locate from the surface, but that the low-frequency sounds it produced, the hum of its machinery, the slow rotation of its propellers, would propagate through the SOFAR channel across enormous distances. The physics did not distinguish between a submarine and a volcanic eruption. Any sufficiently powerful low-frequency sound source, positioned at or near the channel's central axis, would send acoustic energy outward through the corridor in all directions, losing very little intensity as it went. A listening station positioned within the same channel, thousands of kilometers away, could detect that signal. What the Navy needed was to place listening stations within the channel, connect them to shore-based analysis facilities, and listen. The program that resulted from this understanding was called the Sound Surveillance System. Its development began in the early 1950s, and over the following decade and a half, the Navy deployed a network of seafloor hydrophone arrays at multiple locations around the Atlantic and Pacific basins. The cables connecting these hydrophone arrays ran to shore stations where analysts monitored the incoming signals. Each signal was printed onto a paper readout that scrolled continuously off a reel-to-reel machine, displaying the acoustic environment of the ocean as a visual record, time on one axis, frequency on the other, with the intensity of any given sound represented by how dark a mark it left on the paper. In 1960s shore facilities, the analysts who sat before these readouts were trained primarily to recognize the acoustic signatures of Soviet submarines, the particular frequency profiles and rhythmic patterns that identified a specific vessel type, or even a specific boat. The work was precise, patient, and deeply classified. What those analysts also saw, scrolling past on the same paper readout alongside the submarines and the ships, were signals that no one had put there and no one immediately recognized. Some of these were geological, the acoustic energy of distant earthquakes arriving through the channel as a particular kind of signal called a T-phase, a long-distance cousin of the seismic waves that instruments on land were already recording. Some were biological, the low sustained calls of fin whales and blue whales, which produce some of the most powerful sounds of any animal on Earth, propagating through the channel across ocean basin distances. And some were neither, or at least could not be immediately placed into either category. An analyst at one of these facilities might mark such a signal with a pencil note in the margin of the readout, a question mark, or a phrase like unknown biological, or simply a notation of the time and frequency range, a signal worth returning to. Most of these annotations were never followed up systematically. The system had been built to track submarines, and that was what it was primarily organized to do. The anomalous signals that were not submarines, not whales, not earthquakes, these were noted, sometimes briefly discussed, and then the readout scrolled on, and there was more to attend to. This changed, slowly, after the Cold War ended. The specific date at which the military's grip on the SOFAR network began to loosen is not a single moment, but a process, a series of policy decisions through the late 1980s and into the 1990s that gradually made portions of the network available for civilian scientific use. The National Oceanic and Atmospheric Administration, known as NOAA, was among the institutions that moved to take advantage of this access. NOAA's Pacific Marine Environmental Laboratory, headquartered in Seattle, had scientific interests in the Pacific Basin that made the SOFAR channel's long-range listening properties directly useful. The agency was studying underwater volcanic and seismic activity, biological sound production, and the general acoustic environment of the Pacific. And a network of deep ocean hydrophones capable of detecting low-frequency events across ocean basin distances was exactly the kind of instrument the work required. NOAA's own hydrophone deployment program began in earnest around 1991. The autonomous hydrophone stations the agency deployed were different in some respects from the Navy's original SOFAR arrays, designed to operate independently without direct cable connections to shore, recording acoustic data onto internal storage systems that could be retrieved when the instruments were periodically recovered and serviced. The equatorial Pacific became the initial focus of deployment, with instruments positioned to achieve overlapping acoustic coverage across a broad stretch of the basin. Through the mid-1990s, the array expanded, adding stations and extending the geographic range of coverage until a single acoustic event in one part of the Pacific could be detected simultaneously at multiple stations spread across the basin. The scientific value of this kind of simultaneous multi-station detection was not merely that it allowed researchers to identify that a sound had occurred, it was that it allowed them to locate where the sound had occurred. Sound traveling through the SOFAR channel arrives at geographically separated stations at slightly different times because the signal takes longer to reach a station that is farther from the source. By measuring these tiny time differences, in some cases differences of only a few seconds across distances of thousands of kilometers, researchers could triangulate backward to a probable source location. The precision of this triangulation depended on how many stations detected the signal and how accurately their positions and clocks were known. But with a well-maintained array, the technique was capable of placing an acoustic source within a few hundred kilometers, specific enough to identify ocean basin geography, tectonic features, and in some cases, the approximate position of active volcanic zones. The sounds that arrived at these instruments were not all surprising. A significant fraction of what the NOAA hydrophone array recorded in any given period was well understood before the data was even collected. Cargo ships moving through the Pacific produced a characteristic low-frequency rumble, recognizable from the rhythm of their propeller rotation and the frequency range of their engine noise. Earthquakes produced T-phase arrivals, whose timing, frequency, and spatial pattern corresponded reliably with events that seismographs on land were recording simultaneously. Fin whales called at frequencies around 20 Hz, their calls identifiable by their specific tonal quality and temporal pattern, their locations trackable through the same triangulation methods used for geological events. Sperm whales produced short, sharp clicks at somewhat higher frequencies, a different acoustic signature, arriving as rapid sequences rather than sustained tones. Against this background of recognizable sounds, the signals that could not be attributed to known sources stood out with reasonable clarity. They had frequency profiles or temporal patterns that did not match the cataloged signatures of known geological, biological, or human-made sources. They appeared at unexpected times, or from unexpected geographic directions, or with acoustic characteristics that no known process had been documented to produce. The NOAA acoustics team developed procedures for handling these signals, cataloging them, noting their characteristics carefully, assigning them informal descriptive names derived from what their spectrogram representations looked like, or from some distinctive quality of the sound itself, when pitch shifted to frequencies the human ear could hear. A spectrogram is a visual representation of sound over time. The horizontal axis represents time moving from left to right, and the vertical axis represents frequency, with lower frequencies near the bottom and higher frequencies near the top. The intensity of a signal at any given moment and frequency is represented by brightness or color, with stronger signals appearing as darker or more saturated marks on the display. What this means in practice is that a sustained tone at a constant frequency appears as a horizontal line. A tone that rises in frequency over time appears as a diagonal line, moving upward from left to right. A brief broadband event, an explosion, a crack, a sudden impact, appears as a vertical smear. A more complex sound produces a more complex visual pattern. The researchers who first began cataloging anomalous NOAA hydrophone signals would pull up a spectrogram on a monitor in Seattle and look at the shape of the signal before they did much else. The shape was often the most immediate thing, an unusual pattern, a line going in an unexpected direction, a temporal structure that did not resemble the familiar shapes of whale calls or seismic T-phases. They would reach for a logbook and make an entry, the date, the station, or stations that detected the signal, the frequency range, the duration, and some description of its visual appearance on the spectrogram. Then they would give it a name. The names were practical and informal, the kind that researchers use in working conversations before a phenomenon has been studied long enough to acquire technical nomenclature. The names described what the researchers saw or what they heard when they listened to the pitch-shifted audio or where the signal seemed to come from. The ocean that these instruments were listening to was not quiet, even in the absence of ships, biological sound, and geological events. The deep Pacific had its own ambient noise, a low continuous murmur arising from many sources simultaneously. Surface waves breaking and interacting with each other far overhead produced a particular kind of acoustic energy that propagated downward into the ocean and arrived at so far depth as a diffuse, low-level background signal. Distant storms contributed to this background. The slow movement of water masses added to it. At so far depth in the equatorial Pacific, this ambient floor was not unpleasant, a constant, undifferentiated low sound, quieter than the background noise of any inhabited place on land, present simply because it was generated by the ocean in all directions, and there was nowhere in the ocean, at any depth, that was entirely free of it. It was against this background that the NOAA hydrophone network spent its first full year recording The array's instruments collected acoustic data continuously, not sampling periodically, but recording the full ambient sound environment through every hour of every day, through shipping traffic and seismic events and whale migrations and whatever else the Pacific sent their way. The data came back to Seattle when the instruments were periodically serviced, and researchers worked through it systematically, cataloging, identifying, setting aside the unresolved signals for further examination. The equatorial Pacific was, in many respects, a remarkable location for this kind of listening. The SOFAR channel in this part of the ocean sits at relatively shallow depth, its central axis closer to 800 or 900 meters than the one 200 meters it reaches at higher latitudes, and the channel's acoustic properties in this region allow it to receive signals propagating from a very wide range of source locations around the Pacific Basin. A geological event near the Aleutian Islands would send its T-phase southward through the channel toward the equatorial array. A biological sound produced by blue whales in the Southern Ocean would propagate northward along the same corridor. An acoustic event originating near one of the Pacific Basin's active spreading ridges, the chains of undersea volcanic activity, where new oceanic crust was forming along linear fissures in the seafloor, would travel outward through the channel in all directions and arrive at the equatorial array from whatever compass direction the source lay. The Pacific Basin contains several of these spreading ridges. The East Pacific Rise runs roughly north to south through the eastern Pacific, a line of volcanic activity marking the boundary between tectonic plates that are slowly pulling apart, with new basaltic rock welling up to fill the gap at a rate of a few centimeters per year. The Pacific Antarctic Ridge runs through the southern Pacific between South America and Antarctica, another spreading center in one of the most remote stretches of open ocean on Earth. Along these ridges, volcanic and hydrothermal activity is continuous, magma moving through chambers and conduits beneath the seafloor, superheated water circulating through cracks and fissures in the new rock, the steady mechanical process of crustal formation generating low-frequency acoustic energy that propagates upward into the water column and outward through the SOFAR channel. The instruments the NOAA team deployed were sensitive enough to detect this geological background. A large submarine earthquake along a spreading ridge would produce a strong, unmistakable T-phase signal. A smaller volcanic tremor event, the sustained low-frequency vibration associated with fluid movement through subsurface conduits, would produce something subtler, a long, low signal at frequencies below 100 Hz, persisting for minutes or hours, traveling through the SOFAR channel toward the equatorial array, and arriving as a quiet but detectable electrical response in the transducer. Most of this geological background was identifiable. The frequency ranges, temporal patterns, and geographic directions of known geological processes were well enough established by the early 1990s that a seismically trained ear could recognize them in the data. What could not be immediately recognized was set aside. The logbook accumulated entries. The names were written down. The instruments continued to listen, moored at SOFAR depth in cold, dark water, their transducers registering every pressure variation that passed through the channel, recording everything, distinguishing nothing on their own, leaving the work of recognition entirely to the researchers in Seattle. The most important property of the SOFAR channel for all of this work was simply the distance over which it could carry a sound without losing detectable intensity. In air, a loud sound loses most of its energy within a few kilometers. The acoustic wave spreads outward in 3 dimensions, and the energy per unit area decreases as the square of the distance from the source. In the SOFAR channel, The spreading is constrained. The channel's refractive properties trap acoustic energy within the horizontal layer, and in this constrained geometry, the intensity falls off much more slowly with distance. A sufficiently powerful low-frequency sound source, a large earthquake, a major volcanic event, something producing sustained acoustic energy in the right frequency range, can send a detectable signal not just across 100 kilometers or 1,000, but across the full width of an ocean basin. The width of the Pacific Ocean at the equator is roughly 17,000 kilometers. A sound traveling through the SOFAR channel at approximately 1,500 meters per second covers this distance in about 3 hours. The same sound traveling through open air would lose detectable intensity long before it reached the far shore of any significant body of water. In the SOFAR channel, given the right source and the right frequency, the signal arrives. It is weaker than it was when it left its source. Nothing travels without some loss, but it is still there, still coherent, still carrying in its frequency profile and temporal structure the information that identifies where it came from, and with careful analysis, something about what produced it. This was what the hydrophone network had been built to detect. For the Navy, the signals of interest were submarines, specific, engineered, human-made acoustic sources. For NOAA's researchers, the signals of interest were broader. Anything that the ocean produced, known or unknown, geological or biological, or somewhere in between. The transition from a classified military network to a tool for civilian ocean science did not change the fundamental physics of what the instruments could hear. It changed only who was listening and what they were listening for. The research vessel that lowered the first NOAA autonomous hydrophone in 1991 returned to its mooring after the deployment was complete and left the instrument there in cold, dark water at so far depth to listen on its own. The crew could hear nothing of what the hydrophone recorded as they worked on deck above. The frequencies involved were too low, the water column too far above the transducer, and the instrument's electrical signals were traveling into a storage system inside the pressure casing, not broadcasting back to the surface in any form the crew could receive. What the instrument recorded in its first hours of operation was, by the standards of what would follow, unremarkable. A distant ship, sperm whale clicks arriving from the north. The low geological background of the equatorial Pacific, the slow murmur of a seismically active basin going about its ordinary business. The sounds of an ocean that had been making these sounds long before any instrument existed to record them, and that would continue making them long after any particular instrument was recovered and replaced. The channel through which these sounds were traveling had been there long before the Navy's listening program, and long before the oceanographic theory that explained it. It had been carrying acoustic energy across the Pacific Basin for as long as the Pacific Basin had existed in something like its current form, which is to say for tens of millions of years, across ocean basins, shaped and reshaped by the same tectonic processes, whose acoustic signatures the NOAA array was now for the first time systematically recording. A sound produced at the Pacific-Antarctic Ridge in the Southern Ocean could travel northward through this corridor for thousands of kilometers, passing beneath the equatorial array and continuing on toward the northern Pacific, arriving at the far shore of the basin days after it was produced. The time delay depended on the exact distance traveled and the exact speed of sound in the channel along that particular path. Sound velocity varies slightly with temperature and salinity, and the specific route a signal takes through the basin affects how long it takes to arrive. But the signal would arrive. A sound made on one side of the Pacific, under the right conditions, could still be detected at an instrument on the other side. Not immediately, and not without the considerable engineering effort that had gone into making instruments sensitive enough to detect what remained of the signal after that journey, but detectable. This was when the NOAA team began working with it seriously in the early 1990s, a genuinely striking physical fact. The ocean was not merely a medium through which sound traveled locally. It was, in the right frequency range and at the right depth, a medium through which sound traveled continentally, across distances that made the acoustic environment of one end of the Pacific Basin directly connected, in a physical and recordable sense, to the other. What happened geologically or biologically near Antarctica could, if it was powerful enough and at a low enough frequency, announce itself to an instrument moored near the equator days later, still carrying enough energy to leave a clear mark on a spectrogram in Seattle. The SOFAR channel, lying at roughly 800 meters depth across the equatorial Pacific on a calm, clear day, is invisible from above. Looking down into the ocean from the deck of a ship, a researcher would see surface water, then the changing colors of depth, then nothing. The light fails before reaching even a fraction of the channel's depth. But the channel is there, a horizontal layer of slowed sound running through the interior of the ocean, like a river set inside a river, carrying acoustic energy from west to east, and east to west and north and south, simultaneously, in all directions at once, at roughly 1,500 meters per second, from sources separated by half an ocean, toward instruments that were built precisely to receive what the channel was carrying. At this moment, in the water under the research vessel, a sound that began somewhere far to the south is still traveling. It will take hours yet to arrive at the nearest listening station, and when it does, the instrument will register it, and something that happened in the deep water of the far southern Pacific will become, for the first time, a fact that a person in Seattle can read. On a monitor screen in a research facility in Seattle, a spectrogram is open. The display shows frequency on its vertical axis and time running left to right, and across the middle of the image there are lines, short lines, each one angled upward from left to right, rising from a lower frequency to a higher one over the course of a few seconds, then stopping. Then another begins, slightly offset, making the same climb, then another, arranged across the display like the marks left by a pen lifted and set down again, lifted and set down, each stroke tilted at the same gentle angle. They are narrow and clean. They do not waver. Whatever made them was doing something consistent, something that repeated with a kind of patience that left a visible record on the screen. The year was 1991. The hydrophone array had been recording for only a short time, and among the first things it captured, alongside the distant rumble of passing ships and the clicks of whales moving through the equatorial Pacific, was this, a sound no one had catalogued, a sound that looked on a spectrogram like a series of small waves moving steadily across a page, each one rising. They called it Upsweep. The name came from that visual signature, the upward slope of each tonal line, the way the frequency rose and kept rising for a few seconds before the tone ended and the next began. Naming sounds in this program was practical rather than poetic. Researchers looked at the shape a signal made on a spectrogram and found the word that described it most directly. The shape here was unambiguous. Something was sweeping upward. Something was doing it repeatedly. And whatever it was doing it from somewhere far away, sending its signal through thousands of kilometers of open ocean water before it reached the instruments that caught it. A hydrophone at the depth where it was moored receives what the ocean sends. It does not ask where a signal comes from before it records it. It registers the change in pressure as the acoustic wave passes through, converts that mechanical event into an electrical one, and the electrical signal is recorded and stored. The instrument does not evaluate. Later, the humans looking at what was recorded do the evaluating, and what they saw in this case was a pattern. Short rising tones, a few seconds each, repeated across time, repeated again the following spring, and the spring after that. Upsweep was not a single event, it was a recurring one. The first thing researchers noticed after naming it was the seasonal shape of its presence. Not a constant signal, not something that arrived once and faded. Its amplitude, the strength of the signal, the degree to which it stood above the ambient noise floor of the ocean, rose reliably during spring and autumn and declined during the months in between. This happened across multiple years of monitoring. The same rough pattern, the same rough timing, cycling through the calendar with a regularity that made it clear this was not random. Something was producing this sound on a schedule, or at least on a cycle, tied somehow to the turning of the year. That seasonal regularity is one of the things that makes Upsweep distinctive among the recordings in NOAA's catalog. A sound that appears once is a puzzle with no edges. A sound that appears every year, reliably, at roughly the same time, is a puzzle with structure. The structure does not explain the sound, but it narrows the field considerably. Random geological events do not repeat seasonally. Random equipment faults might, if they correlate with temperature changes or maintenance cycles, but those can be checked and ruled out. Biological sources sometimes follow seasonal patterns, migrations, breeding seasons, the rhythms of animal behavior tied to light and temperature, but the frequency range of Upsweep, sitting between roughly 40 and 80 hertz, is lower than most biological vocalizations that have been characterized in the scientific literature, and the signal's acoustic character, those narrow, consistent, rising tones, does not match the calls of any known marine animal. At 40 to 80 hertz, a sound is very low, lower than the lowest notes on a standard piano keyboard, lower than most of what a human ear would perceive as a distinct tone, rather than a felt vibration. When recordings like Upsweep are pitch shifted upward to make them audible to human listeners, the rising quality of each tone becomes audible as a brief ascending note, a short upward slide, and the sequence of them produces something that resembles, faintly, a pattern of calls. But there is no known animal making them, and the acoustic properties of the signal do not fit the production mechanisms of marine mammal vocalizations. The tones are too narrowband, too consistent in their rate of frequency rise, too regular in their repetition across time. What occupies the 40 to 80 hertz range efficiently is geological activity, submarine earthquakes, volcanic tremor, the movement of fluid through conduits in the seafloor. These processes generate low-frequency acoustic energy that couples into the water column and travels efficiently through the layer of the ocean where sound propagates most effectively. The zone, sitting roughly between 600 and 1200 meters depth, where the velocity of sound reaches a local minimum and acoustic energy bends continuously back toward the axis rather than spreading outward and dissipating. Within that zone, low-frequency signals can travel enormous distances while retaining enough intensity to be detected. Upsweep's signal, at the frequencies it occupies, is well suited to exactly this kind of long-range propagation, which is how it could be heard at all, given where it appears to come from. Acoustic triangulation is the method by which researchers estimate the location of an underwater sound source. Because sound travels through seawater at a known speed, roughly 1,500 meters per second, varying with temperature, salinity, and pressure, a signal arriving at multiple geographically separated hydrophone stations will arrive at each station at a slightly different time. Those time differences, measured precisely, can be used to calculate the direction from which the signal came. Data from multiple stations, triangulated together, can narrow the source to a region rather than a single point. The region for Upsweep, identified through this process, is a stretch of ocean in the far southern Pacific associated with the Pacific Antarctic Ridge. The Pacific Antarctic Ridge is a spreading center, a boundary between tectonic plates where the seafloor is being pulled apart and new oceanic crust is forming. Along this ridge, volcanic activity is ongoing and continuous, driven by the upwelling of material from the mantle below. The ridge runs through one of the most remote stretches of open water on the planet. There are no nearby coastlines, no ports within reasonable reach. The nearest land, in most directions, is measured in thousands of kilometers. Research vessels have visited, but sustained presence in these waters is difficult, and the seafloor below, the volcanic terrain where Upsweep's source is thought to be located, has not been directly investigated in connection with this sound. The leading scientific hypothesis for Upsweep proposes that it is generated by volcanic tremor. Volcanic tremor is a particular kind of seismic signal, not the sudden rupture of an earthquake, but a sustained low-frequency vibration produced by the movement of fluid or gas through conduits within volcanic rock. Magma moving through a chamber, superheated water moving through a lava tube under pressure, gas accumulating and releasing through a hydrothermal vent. These processes produce vibrations that are continuous rather than impulsive, and that occupy frequency ranges well suited to long-range acoustic propagation through seawater. The picture, as the hypothesis goes, looks something like this. Somewhere along the Pacific Antarctic Ridge, a volcanic system is active. Within that system, some geometry of rock and fluid is generating a resonance, a sustained vibration at a rising frequency, lasting a few seconds, then repeating. The specific rising quality of each tone, the upward sweep that gives the sound its name, would reflect the changing physical conditions of the resonating system as pressure builds and releases, or as the geometry of the conduit shifts slightly, causing the frequency of the vibration to rise as the sound is being produced. The seasonal variation in amplitude might reflect seasonal changes in how efficiently the acoustic energy produced at the volcanic source couples into the water column and enters the long-range propagation pathway, shifts in temperature, in current patterns, in the physical conditions at the boundary between the geological source and the ocean. This is a plausible explanation. The pieces fit together in a way that is scientifically coherent. Volcanic tremor is a known phenomenon. Seasonal acoustic coupling variations are consistent with known oceanographic processes. The location identified by triangulation is volcanically active. The frequency range of the signal is consistent with what volcanic systems produce, but plausible is not confirmed. The record of Upsweep goes back more than 3 decades now. The hydrophones have been listening continuously for all of that time, and every spring and every autumn the signal returns, still making those same rising tones, still arriving at the instruments with the same patient regularity it showed in the first year it was recorded. The monitoring has continued. The data has accumulated. The signal has not provided, in all that time, any additional information that has allowed researchers to move beyond the hypothesis to something firmer. The source region has not been visited specifically to investigate Upsweep. No direct measurement of the seafloor conditions in that region has been made in connection with this sound. The identification of volcanic tremor as the likely mechanism remains a working explanation, not a confirmed one. NOAA classifies upsweep officially as an anomalous sound of unknown origin. The classification is not a failure. It is the honest state of the record. There is a particular quality to the experience of monitoring something for 30 years without resolving it. The scientists who first saw Upsweep's signature on a spectrogram in 1991 noted it, named it, began gathering data on it, and then continued. Other work continued alongside it. The array kept recording. The catalog of sounds kept growing. The seasons kept turning. And each spring, when the spectrogram data came in and the familiar pattern appeared, those short rising lines, the same angle, the same frequency range, the same narrowband character, it was both familiar and still open, still a question. A researcher who has been watching the same seasonal pattern arrive for 15 springs has by some measure a different relationship to that question than someone who saw the signal once and moved on. The pattern becomes a kind of annual event, in something expected, something that arrives, something that is noted with the same steady attention it always receives. Not urgency, not resolution, just the ongoing fact of a signal still doing what it has always done, still not fully explained, still arriving. Imagine the spectrogram display on a monitor in a quiet room. The researcher opens it during the spring monitoring period, the time of year when Upsweep's amplitude is typically highest, and the rising lines are there. 15 years of seeing this, or 20, and still the same image appears. The lines are short, they angle upward, they are narrow and clean. The signal is doing exactly what it was doing in 1991, unchanged in its character, consistent in its timing, unresolved in its origin. There is something almost comfortable in that consistency, even as the question it represents remains open. The Pacific Antarctic Ridge, several thousand meters below the ocean surface, is not a still or quiet place. New crust is forming along it continuously, pushed up through the fissure where the plates are separating, cooling as it meets the water, building outward from the spreading center at a rate of centimeters per year. Along the ridge, hydrothermal vents release superheated water rich in dissolved minerals, and around those vents, communities of organisms have adapted to conditions that bear little resemblance to the sunlit ocean above. Below the seafloor surface, through the porous and fractured rock of the volcanic terrain, fluids move under pressure, water heated by the contact with hot rock, gases rising through conduits, material in a state of perpetual slow movement, driven by the heat of the earth below. If something in that geometry is generating upsweep, it has been generating it for at least 30 years, with no sign of stopping. Volcanic systems can persist at a relatively stable level of activity for very long periods. A lava tube that has been carrying fluid at a certain pressure for decades will continue to do so as long as the conditions driving it remain constant. A hydrothermal system that has been operating for a century may show very little change from year to year, decade to decade. Its acoustic signature, a steady low murmur against the geological background. The seasonal variation in Upsweep's amplitude is in this light the most interesting feature of the signal. If the source is a volcanic system operating continuously, why would its acoustic signature at the hydrophone stations vary seasonally? The volcanic activity itself is not thought to be seasonal. There is no known mechanism by which tectonic processes would cycle with the calendar year in the way Upsweep's amplitude does, which suggests the variation is not in the source, but in the path. The conditions through which the sound travels, the temperature of the water, the depth and character of the propagation layer, The seasonal shifts in ocean currents and stratification may change in ways that alter how efficiently a continuous low-frequency signal is carried from the southern Pacific to the hydrophone stations in the equatorial Pacific. Ocean stratification is not constant. The structure of the water column, the way temperature, salinity, and density vary with depth, shifts across the year in response to seasonal heating and cooling, wind-driven mixing, and changes in circulation patterns. These shifts affect the acoustic properties of the water. The sound produced at a given depth and frequency will propagate differently through water whose thermal structure has changed, even if the source is producing the same sound at the same intensity. The SOFAR channel's efficiency as an acoustic conduit changes somewhat with the seasons. If Upsweep source is continuous, but the propagation path is seasonal, the result at the receiving instruments would be exactly what is observed, a seasonal variation in received amplitude without a corresponding variation in the source itself. This is another coherent piece of the hypothesis. It fits the data, and it remains, as the whole explanation does, a working model rather than a confirmed account. The distance from the probable source region to the equatorial Pacific hydrophone array is several thousand kilometers. Sound traveling through the SOFAR channel at roughly 1,500 meters per second, a speed that varies with the physical conditions of the water, but falls roughly in that range, takes hours to cover that distance. A tone produced at the Pacific Antarctic Ridge in the late afternoon arrives at the equatorial Pacific hydrophones in the early hours of the following morning, still detectable, still carrying the upward rising frequency profile that it had at the moment of its production. The ocean has carried it that entire distance without absorbing enough of its energy to make it disappear. It arrives changed, attenuated, its higher frequencies stripped away more readily than its lower ones, its waveform affected by the acoustic conditions it passed through, but it arrives. That arrival, that persistence across thousands of kilometers of cold, dark water is worth pausing on. The signal was produced by some process in the rock of the seafloor beneath the southern Pacific. It entered the water column and found its way into the propagation layer. It traveled northward through that layer, guided by the gradient of sound velocity, bending back toward the axis whenever it drifted away from it, traveling efficiently in a way that a higher frequency signal would not. And at the end of that journey, a pressure-sensitive instrument registered the small mechanical event of its arrival, and the record was made. The instrument does not know what it recorded. The record is a trace on a display, a series of numbers in a file, a set of rising lines on a spectrogram. What those lines represent? The physical process at the volcanic source, the specific geometry of the conduit or chamber or vent that set the water vibrating at those frequencies in that rising pattern, remains out of reach. The record is complete. The explanation is not. A research vessel positioned over the Pacific Antarctic Ridge sits in water that is among the roughest and most remote on Earth. Southern ocean swells have crossed thousands of kilometers of open water to arrive at that location, and in heavy weather the vessel moves with the rhythm of seas that built their energy over a vast fetch. Below the hull, the water column extends downward for several thousand meters before the rocky terrain of the ridge appears. Below the ridge surface itself, the volcanic rock is fractured and permeable, laced with conduits and chambers through which fluid moves under the pressure of the heat below. The seafloor here has not been directly investigated in connection with Upsweep. The vessel, even moored above the probable source region, would be separated from the origin of the sound by kilometers of rock and water that no current instrument can penetrate with the resolution needed to identify a specific resonating structure. This is the physical reality of the open question. The inaccessibility is not a failure of will or resources. It is a straightforward consequence of the environment. The deep sea floor in remote ocean regions is, in practical terms, among the least accessible surfaces on the planet. Sending instruments to the seafloor requires significant logistical effort, and even instruments successfully deployed on the seafloor cannot see into the rock below it. The source of upsweep, if it is volcanic, is within the rock, within the lava tubes and magma conduits that cannot be directly observed from the outside. Acoustic triangulation can point toward a region. It cannot resolve what is happening within the rock of that region at the scale of meters. So the listening continues. The instruments remain at their moorings, suspended at depth in the equatorial Pacific, registering the pressure fluctuations that pass through them. The data is transmitted and stored and reviewed, and each spring, when the rising lines appear again on the spectrogram, the same patient process of noting and recording begins again. The sound comes, the record grows, the question stays open. There is a way of thinking about long-term scientific monitoring that is not about the expectation of resolution. Some questions are held not because an answer is imminent, but because the question is worth holding. Upsweep was detected in 1991, named, and has been monitored since. The monitoring has not resolved it. That fact alone, that something has been listened to for more than 30 years without explanation, is a form of knowledge. It establishes that the signal is persistent, that it is seasonal, that it occupies a consistent frequency range, that it comes from a consistent general direction, that it has not changed significantly in character across 3 decades of observation. All of that is known. The mechanism is not. The lines on the spectrogram from 1991 look the same as the lines from this year's spring monitoring period. Same angle, same frequency range, same narrowband quality. Something beneath the southern Pacific has been making that sound for at least as long as instruments have been in place to catch it. And the instruments have been in place long enough that 1 or 2 generations of researchers have come to regard its spring arrival as something almost like a seasonal constant. Not quite a certainty, acoustic conditions vary, and in some years the signal is harder to detect than others, but a reliable feature of the annual monitoring record. The sound that rises every spring, still rising, still unresolved. Somewhere in the cold water of the southern Pacific, well below the surface and well north of the Antarctic, the sound is in transit right now, or something like it is. A rising tone, narrow and consistent, produced by some process in the volcanic rock of the sea floor, beneath one of the most remote stretches of ocean on the planet. It entered the water column. It found the propagation pathway. It is moving northward through the dark water at a depth of several hundred meters, guided by the gradient of sound velocity, losing some of its intensity to the water as it goes, but losing it slowly, losing it in the way that only low-frequency sound in the right channel can afford to lose it, gradually, across a distance that would take a ship many days to cover. The instruments are waiting. They have been waiting since 1991. They will register the signal when it arrives, add it to the record, and the record will grow by another season's worth of rising lines. The sound will have made its journey again, and the question of what, exactly, is producing it in the rock below the ocean floor of the Pacific Antarctic Ridge will remain where it has been for more than 30 years, open, patient, genuinely interesting, requiring no resolution tonight. The spectrogram from the next spring monitoring period will look, in all probability, very much like the one from this year, and the one from this year looks very much like the one from 1991. The rising lines will be there, short, narrow, clean, tilted upward at the same gentle angle. Whatever is making them does not appear to be in any hurry. Neither, it seems, is the question. The ocean holds Upsweep the way it holds all of its long-running processes, without particular interest in being observed or understood, simply continuing, the sound rising every spring in the cold dark water below the southern Pacific, traveling northward through the channel where low-frequency acoustic energy moves efficiently across the basin, arriving at instruments that register its presence with the same steady attention they have brought to it since the first year. It appeared on a screen in Seattle, and someone reached for a logbook and wrote down a name for it. The sound is still rising. It has been rising in this patient and seasonal and genuinely unresolved way for more than 3 decades. Next spring, it will almost certainly rise again. The same upward sweep, the same frequency range, the same acoustic signature making its way from wherever it begins, through thousands of kilometers of water, to the instruments that are still, quietly listening for it. On the morning of March 1st, 1999, a recording instrument in the equatorial Pacific registered a change in pressure. The change was small in absolute terms, a minute fluctuation in the electrical output of a submerged transducer, the kind of signal that appears on a readout as a thin rising line against the quiet background of ambient ocean noise. The instrument logged it automatically, somewhere in the data stream flowing back to a monitoring station. That line began its journey toward a screen where a researcher would eventually see it, look at it for a moment, and reach for a notebook. What appeared on the readout was a tone. It began at a low frequency and moved upward, not steeply, not in a sharp diagonal, but in a gradual and slightly wandering rise that climbed for a few seconds, held, shifted, and then faded. The visual shape on the spectrogram was not a clean line. It was more like the trace a hand makes when drawing a slope without a ruler, recognizable as ascending, but with a quality of irregularity to it, a subtle wavering as the tone moved through its range. The whole event, from first signal to last, lasted approximately 15 seconds. That was Julia. The name came later, assigned by NOAA researchers following the convention they had developed for anomalous recordings, informal names drawn from the visual character of the spectrogram or some quality of the sound itself, names that were practical rather than poetic, and that stuck because the cataloging work required something to write in the logbook. Julia was unusual enough to earn its entry. The duration was ordinary. The acoustic shape was not. What made the recording immediately notable was not the sound's duration or even its frequency profile in isolation. It was the reach. When the researchers began comparing data from the different hydrophone stations distributed across the equatorial Pacific array, they found the same signal logged at every one of them, not at one station, not at a subset of nearby instruments, but across the full network, geographically separated listening posts, spread over a wide section of ocean, all registering the same acoustic event within moments of each other, the signal's arrival, offset slightly from station to station by the time it had taken to travel the distance between them. A sound audible across an entire ocean basin requires a source of considerable acoustic power or extraordinary efficiency of transmission, or both. Julia apparently had both. The SOFAR channel, that deep horizontal corridor in the ocean where sound velocity reaches a local minimum and acoustic energy refracts back toward the channel axis, rather than dispersing outward, had carried the signal with very little loss across the distance from source to receiver. This is what made the network useful. Sounds originating at the right depth and the right frequency could travel thousands of kilometers and arrive still detectable, still identifiable as a coherent acoustic event, rather than absorbed into the background noise. Julia had used that channel efficiently. Whatever had produced it well. The frequency range sat very low, low enough that in its raw recorded form, the sound was felt as much as heard, occupying the part of the acoustic spectrum where distinctions between sound and vibration begin to blur. When the researchers pitch shifted the recording upward into the range where human hearing is more sensitive, what emerged was a tone with a particular quality, deep, slow, with the slight irregularity that the spectrogram had shown, beginning with some clarity and then wandering as it ascended. It did not sound like machinery. It did not sound like a geological process in any way that was immediately familiar. It sounded to some ears like a voice, or at least like the kind of sound that a very large biological structure might conceivably make. That observation, once made, was difficult to set aside entirely. The early period after Julia's public release involved some genuine discussion, both within research communities and among people following NOAA's Anomalous Sounds catalog, about whether the recording might represent the vocalization of an animal, an undocumented species of considerable size, capable of producing acoustic energy at that frequency and that power. The low-frequency range overlapped with the calls of the largest known baleen whales. The tonal quality, when pitch shifted, had an organic character that was easier to describe than to dismiss. This speculation was understandable given what the recording contained, a 15-second acoustic event of considerable power, arriving from a source that triangulation placed somewhere in the waters near Antarctica, with a tonal shape that didn't match any cataloged geological signal. It was reasonable, in the earliest stages of analysis, to hold the biological possibility open. Large ocean basins contain many things that have not been cataloged. The deep water near Antarctica is not well surveyed. A researcher who refused to consider the biological hypothesis until it had been properly eliminated would have been doing their job correctly. The elimination came, and it was not grudging. As the analysis developed and the research community examined the recording more carefully, the weight of evidence moved clearly toward a physical rather than biological explanation. The acoustic power required to register simultaneously across the full array, from a source in southern ocean waters, was at the upper range of what any biological structure of plausible size could produce. The frequency profile, while superficially organic in character, was consistent with something other than a vocal apparatus working through air-filled chambers, and critically, the probable source region pointed toward a physical environment where something else was happening at that scale. Antarctica, in March of 1999, was doing what it always does in the southern autumn, shedding ice. The ice shelves at the margins of the continent were calving and fracturing, releasing into the ocean the tabular icebergs that drift northward through the Southern Ocean over the months and years that follow. These are not small structures. The largest of them are measured in hundreds of kilometers, floating platforms of compressed ancient ice, their surfaces extending above the waterline and their keels descending hundreds of meters below. They drift slowly, driven by current and wind, and as they move they encounter the seafloor, the Ross Sea, and the broader region of Antarctic waters, where Julia's source was triangulated, sits over seafloor that is complex in its topography. There are shallow sections, ridges, rises, places where the ocean floor comes close enough to the surface that a large iceberg's keel, descending hundreds of meters down from the waterline, makes contact. When that contact happens, what occurs is not a clean impact. It is something more sustained and mechanical, the mass of the ice pressing against the rock as the current continues to push the iceberg along, the keel grinding slowly against the ridge, or the friction of millions of tons of ice against solid seafloor generating stress and vibration that radiates outward through the water as acoustic energy. The scale of this process is worth holding for a moment. A large tabular iceberg carries within it snow that fell on the Antarctic continent decades or centuries before. It has been accumulating since before many currently living people were born, pressing down under its own weight, the air between the snowflakes compressed out over time until what remains is dense ice carrying the record of the seasons in which it formed. When such a structure drifts into a ridge and begins to grind, the mass that is moving is not just the visible ice above the waterline, it is the entire submerged body, hundreds of meters of it, wider than some cities, bearing downward with the weight of everything it has accumulated. The acoustic energy that contact generates reflects the scale of the mass in motion. This is the explanation that achieved broad consensus among the researchers who studied Julia, an iceberg grounding a large ice body, making sustained contact with the seafloor somewhere in Antarctic waters, possibly in or near the Ross Sea region, generating intense low-frequency acoustic energy as the contact stress released through the ice and the water, and that energy traveling northward through the deep water into the Sofar Channel, propagating efficiently across the basin, and arriving at a network of instruments in the equatorial Pacific, still strong enough to register at every station simultaneously. The wandering quality of the tone, the slight irregularity in the rising frequency profile that had given Julia its organic character, was consistent with what happens when a large ice body moves against an irregular surface over time. The contact geometry changes as the ice drifts. The resonant properties of the system, the ice, the water, the rock, shift as the points of contact shift. The acoustic output reflects those changes, not a clean, steady tone, but something that rises and wanders as the physical situation develops. The spectrogram shape that had looked, at first glance, like a voice, was in fact the acoustic signature of a physical process too large to observe directly. Ice is one of the ocean's most prolific sound producers. This fact is not widely appreciated, partly because most of what ice does acoustically happens at depths and frequencies outside ordinary human experience, and partly because the scale of the ice environment makes individual acoustic events hard to attribute to specific causes without dedicated instruments. But a hydrophone positioned in the right location picks up ice constantly, the cracking of sea ice as temperatures change, the deep groan of a glacier moving, the sharp high-frequency snap of a small ice fragment fracturing in cold water, the slow, low rumble of a large iceberg settling as it drifts into a warmer water mass and its edges begin to melt. Each of these processes produces a distinctive acoustic signature, and researchers who work with deep ocean recordings develop a familiarity with ice sound over time, the way a person who lives near a forest learns to distinguish the sounds of different trees and wind. Julia belongs to a broader family of ice-generated acoustic events, recordings in which the source is some form of physical ice process, and the acoustic output reflects the mechanics of that process in ways that can be read from the spectrogram if the interpretation is available. There is a category of ice-generated sound called an icequake, a sudden release of accumulated stress within a large ice body, analogous in its mechanics to an earthquake, but occurring within a glacier or ice shelf rather than within rock. Icequakes produce sharp, intense acoustic pulses that propagate through the water much as seismic T-phases propagate, efficiently over long distances through the deep sound channel. Julia is not an icequake precisely. Its duration is too long, its frequency profile too sustained, and gradual, but it shares with icequakes the essential character of a massive physical structure, releasing energy through its own mechanics. What is specific to Julia, and what earned it a distinct entry in the catalog rather than being filed under a general category, is the particular shape of that 15-second rising tone. The combination of frequency range, duration, tonal quality, and acoustic power, and the way these elements came together in the single recording from March 1st, 1999, produced an acoustic profile that was unusual enough to warrant individual attention. It has not been recorded again in precisely that form, though ice grounding events in Antarctic waters are not uncommon. The precise geometry of ice body, seafloor topography, water depth, and acoustic coupling that produced Julia's particular signature has apparently not recurred in a way that the network has captured with the same clarity. The researchers who worked with this recording were doing something that takes considerable patience and methodological care, and moving from an unexplained acoustic trace toward a working explanation by comparing the signal's properties against the physical processes that could plausibly have produced it, eliminating hypotheses as they became untenable, and arriving at the explanation that was most consistent with the available evidence. This is not a fast process. The initial recording was one data point. The triangulation of its probable source was a second. The examination of the source region's physical characteristics, the seafloor topography, the ice conditions in that area during that period, the acoustic properties of ice grounding at scale, was a third. Each step narrowed the field of plausible explanations and moved the consensus toward the conclusion that eventually held. The conclusion is not certain in the way that a controlled laboratory experiment produces certainty. No one was in the Ross Sea on the morning of March 1st, 1999, watching an iceberg ground against a ridge while measuring the acoustic output. The iceberg that produced Julia, if indeed it was an iceberg grounding, has long since drifted on, calving and melting as it moved into warmer water, leaving nothing to examine. What remains is the recording, a thin trace on a spectrogram, an electrical signal preserved in a data archive, a 15-second acoustic event that traveled thousands of kilometers through dark, cold water to arrive at a set of instruments built to listen for exactly this kind of thing. There is something worth pausing on in the process by which explanation reaches Julia. The network of instruments that captured the recording was not built with icebergs in mind. It was built to listen to the broad acoustic activity of the Pacific Ocean basin, seismicity, volcanism, biological sound, the background noise of a living ocean, with the understanding that a distributed array of sensitive instruments, positioned at depth and maintained over time, would eventually hear things that no one had anticipated. Julia was one of those things. The fact that it registered simultaneously at every station in the array, when many acoustic events are localized to a subset of the network, was itself a piece of data. It told the researchers something about the power of the source before they had any other information about what the source might be. Comparing the readouts from geographically separated instruments is a form of acoustic triangulation, and the precision of that process depends on the care with which the time differences between signal arrivals at different stations are measured. The signal travels through the water at a known velocity, approximately 1,500 meters per second, varying slightly with temperature and pressure. By measuring the difference in arrival time between, say, a station in the Central Pacific and a station near the equatorial East Pacific, the researchers can calculate the angle from which the sound approached each station. Where those angles intersect is the probable source location. The method is not exact. There are uncertainties in the velocity model, and the geometry of the array limits angular resolution, but applied carefully across a well-distributed set of stations, it is capable of placing a source within a region that can then be examined for physical processes consistent with the recording. Julia's source region, defined by this process, pointed toward Antarctic waters. That result, combined with the acoustic character of the recording, the low frequency, the gradual rise, the slight irregularity, and the known physical processes active in that region, pointed toward ice. The biological hypothesis, which had been worth examining, did not survive contact with the full evidence base. The acoustic power required, the source location, the frequency profile, all of these were more consistent with a physical process at the scale of a large ice body than with a biological source of any plausible size. It is worth being clear about what most likely means in a context like this. The iceberg grounding explanation is not the only hypothesis that was considered, and it has not been confirmed by direct observation of the event. What it has is the strongest combination of consistency with the recording's properties, plausibility given the source region's known physical environment, and absence of contradicting evidence. In science, that combination is typically where working explanations rest, not on certainty, but on the convergence of evidence toward a conclusion that is more consistent with the available data than any alternative. What has always made Julia notable, beyond its place in Noah's catalog, is the way it sits between categories. It is not a biological sound, but it was mistaken for one. It is not a volcanic or tectonic event, but it involves the large-scale movement of geological material. In a sense, ice formed from snow, carrying with it the weight of the Antarctic continent's climate over decades. It is not an engineered signal, but it was picked up by engineered instruments specifically designed to catch exactly this kind of long-range acoustic event. It occupies a position that the NOAA catalog is full of, something that turned out to be explicable, but that required careful work to explain, and that along the way revealed something genuinely interesting about the physical world and what it is capable of producing. The world has a great deal of mass and motion at any given moment. The tectonic plates are moving slowly. The ocean currents are circulating continuously. The ice at the poles is drifting, calving, grinding against seafloor ridges in the dark water thousands of kilometers from the nearest inhabited land. Most of that motion is silent from any human perspective, or rather, silent at the frequencies and scales where human perception operates without instruments, but instruments extended into the right environment at the right depth, built to be sensitive to the low-frequency pressure fluctuations that propagate efficiently across ocean basins. Hear all of it. The motion of the world translated into sound. March 1st, 1999 was a specific day in a season of ice movement. The southern autumn brings particular conditions to Antarctic waters, temperature gradients that affect the drafts of large icebergs, current patterns that determine where those icebergs drift and what seafloor features they encounter. The iceberg that may have produced Julia was one of many moving through those waters at that time, and the grounding event, if that is what it was one of many such contact events occurring along the ridges and rises of the Antarctic seafloor. What was unusual was not the event itself, but the acoustic signature it produced, distinctive enough in its properties to register as something categorically different from the background noise, to catch the attention of the people reviewing the data, to earn a name and a place in the record. The recording exists. That is the solid foundation of everything that can be said about Julia. Whatever its source, Whatever the physical process that generated it, the acoustic event happened, propagated through the water, arrived at the instruments, and was preserved. 15 seconds of rising tone, slightly irregular, of considerable acoustic power, originating in the Southern Ocean in the early southern autumn of 1999. The explanation that the research community has arrived at: large iceberg, grounding event, Antarctic waters, is the most consistent with the evidence. It is not the only possible explanation for what the instruments recorded. It is the explanation that holds. The iceberg that produced it, if it did produce it, was already moving when the sound registered at the first station in the equatorial Pacific. The sound had taken some time to travel north through the deep water, propagating at roughly 1,500 meters per second, refracting within the SOFAR channel, losing almost nothing of its intensity over the distance. By the time it arrived at the network, the ice had moved on. The grounding contact, if that is what it was, had either ended or was still continuing, the ice pressing against the rock, the stress releasing, the acoustic energy radiating outward in all directions, a portion of it heading north into the open Pacific, and the rest of it spreading across the Southern Ocean, unrecorded. That is the physical picture, a massive flat structure of old ice, its keel deep in Antarctic water, making contact with the seafloor somewhere beneath the dark surface of the Ross Sea or its neighboring waters. The sound that contact made was not audible to human ears in any ordinary sense. It was a vibration at a frequency below what most human hearing detects as sound, but it moved through the water with the efficiency that low-frequency acoustic energy moves through seawater, and it traveled northward through the SOFAR channel, and it arrived at a set of instruments that converted it into an electrical signal, and that signal was logged, and the log was reviewed, and the trace was named, and Julia entered the catalog where it has remained. After the grounding, after whatever contact produced the sound had ended or shifted, the iceberg continued its drift. This is what icebergs do. They move with the current. They melt at their edges as they reach warmer water. They calve smaller pieces from their margins as stress accumulates and releases. They diminish gradually over months and years until what remains is too small to be tracked by satellite and eventually disappears into the ocean as meltwater. The ice that was once a coherent structure, large enough to produce a sound audible across a basin, dissolves into the water column, distributing itself across a volume too large to measure. The seafloor ridge that the iceberg contacted, if that is the physical picture, remains where it has always been, as it was long before the ice existed, and as it will remain long after. The ridge does not record the contact. The water does not retain any trace of the sound passing through it. What persists is only the electrical signal in the archive, a rising trace on a spectrogram that researchers have examined from multiple angles and placed in the best context available to them. The deep water south of the equatorial Pacific continues to receive sound from the Southern Ocean. Icebergs continue to drift through Antarctic waters, making contact with the seafloor as they always have, generating acoustic energy that propagates into the SOFAR channel and travels northward. Some of those contacts are large enough to register at the network. Some are not. Some produce acoustic signatures similar to Julia's. Some produce something different. The instruments listen to all of it continuously, converting pressure into electrical signal, into data, into an archive that grows steadily larger with each year of monitoring. Julia is one entry in that archive. It is one 15-second event among many thousands of hours of recording, notable for its acoustic character and for the circumstances of its detection, but finally belonging to a physical world that is simply producing these events constantly, in the dark, at a scale and frequency that instruments can hear and human ears mostly cannot. The sound was real. The instrument that caught it was real. The research that produced an explanation was real and careful and modest about its conclusions. On the morning after the recording was made, the ocean continued. The instruments continued to listen. Somewhere in Antarctic waters, the ice that may have produced Julia was still moving, slowly, carrying its accumulated weight northward through cold, dark water, its keel still descending hundreds of meters below the surface, still close to seafloor ridges it might encounter again as it drifted. And in the equatorial Pacific, the hydrophone array registered the next day's sounds, distant ships, whale calls, the low geological murmur that underlies everything else, and the long patient quiet of a deep ocean that has been producing these sounds since long before anyone was listening, and that will continue to produce them long after the instruments are gone. What the recording captured was a moment in a process that has no clear beginning and no expected end. Ice accumulates, drifts, grinds, melts. The acoustic energy of that process radiates outward through the water continuously at low frequencies that travel efficiently through the deep. On one particular morning in 1999, a specific configuration of ice, seafloor, and water produced a particular acoustic shape that arrived, still coherent, at a network of instruments designed to hear it. The instruments did what they were built to do. The researchers did what researchers do. They looked at what they had, considered the possibilities carefully, and arrived at the most consistent explanation they could find. The iceberg, by now, is water. The sound it made that morning is still in the archive, and somewhere in the Southern Ocean, in water that is near freezing and almost perfectly dark below 200 meters, another large structure of old ice is drifting slowly through the current, its keel moving through the deep water above ridges and rises of Antarctic seafloor, carrying within it the weight of seasons long past, going about its own unhurried existence, unobserved, unrecorded, simply continuing the physical process that Julia, on one morning out of many, made briefly and faintly audible. On a spectrogram display, the line descends. It begins somewhere in the upper left of the frame and moves, over the course of 7 minutes, in a smooth and unbroken slope toward the lower right. No sudden drops, no plateaus, no interruptions of any kind. Just a single continuous line traveling steadily downward across the page at a pace that is almost leisurely, like something settling rather than falling. A researcher encountering it for the first time would notice its shape before anything else, the visual cleanliness of it, the way it looks almost too deliberate, too smooth for something that emerged from the random acoustic environment of the deep ocean. It resembles, more than anything, a line someone drew with a ruler. The sound behind that line was recorded on May 19, 1997. NOAA's autonomous hydrophone array in the equatorial Pacific picked it up across multiple stations, and when the recordings were reviewed and the spectrogram produced, researchers saw what that visual shape suggested, a tone that began at a relatively higher frequency and descended gradually and without pause for approximately 7 minutes before fading from the instruments entirely. The sound's descriptive name came directly from what that line does. It slows down, or rather, the frequency descends, which is how slowing works in acoustic terms, a lower frequency being a longer, slower wave, and so the researchers who cataloged it called it slow down, and the name has stayed. The frequency range it occupied was low, deep in the way that matters for acoustic travel, through seawater low enough to couple well with the physical conditions of the water column and move efficiently through the ocean's natural long-range acoustic corridor, which sits at a depth of several hundred meters below the surface, where sound velocity reaches a local minimum and acoustic energy bends back toward the channel axis rather than dispersing outward. A sound in the right frequency range, generated with enough acoustic power, can travel thousands of kilometers through that corridor and still arrive at an instrument as a detectable signal. Slowdown had that property. The hydrophone stations that recorded it were not in the southern Pacific, they were in the equatorial Pacific, and yet the signal arrived clearly enough to allow the researchers to work backward, measuring the tiny differences in arrival time between stations, and estimate where it had come from. That process, acoustic triangulation, involves careful arithmetic applied to very small numbers. The difference in arrival time between two hydrophone stations, separated by hundreds of kilometers, might be a matter of seconds. The difference between stations separated by a shorter distance might be fractions of a second. Researchers compare these offsets, calculate what position would produce those timing relationships, and arrive at a probable source region. The answer is never a point on a map. It is a region, sometimes a broad one, with an estimated center and a margin of uncertainty that can span hundreds of kilometers. For slowdown, that calculation placed the probable source in the southern Pacific Ocean, in the broad vicinity of a feature called the Eltanen Fracture Zone. The Eltanen Fracture Zone is a long, complex structure in the southern Pacific seafloor formed over millions of years by the slow lateral movement of tectonic plates grinding past one another along a transform boundary. The seafloor in that region is deeply irregular, cut by parallel ridges and troughs running roughly east to west, separated by abyssal depths and punctuated by the rough topography that transform faulting produces over geological time. It is not a geologically quiet place, though it is one of the most acoustically remote stretches of ocean on Earth, far from major shipping lanes, and far enough south that biological sound from large marine mammals is relatively infrequent. The ambient noise floor in that region is low. When something produces a signal there, it arrives at the distant hydrophone array without much competition from other sources, and the researchers can hear it clearly against the quiet. What produced Slowdown's particular acoustic signature, a smooth, continuous, 7-minute descent in frequency, is a question that has not been fully resolved. The explanation that NOAA researchers find most consistent with the data involves ice, specifically a large iceberg interacting with the seafloor. In the southern Pacific, at the latitudes where Slowdown was likely generated, icebergs calve from the Antarctic continent and drift northward, carried by circumpolar currents until they enter warmer water and begin to melt. Some of these icebergs are very large, not unusually large by Antarctic standards, where tabular icebergs can span hundreds of kilometers and carry keels that extend several hundred meters below the waterline. As one of these large ice bodies drifts over irregular seafloor topography, its submerged keel can make contact with ridges and shelves of rock. The interaction between that keel and the seafloor as the iceberg continues to drift, or as the geometry of contact shifts under the iceberg's own movement and rotation, can generate sustained low-frequency acoustic energy. The specific frequency decrease recorded in Slowdown is what the ice hypothesis needs to account for. A sustained, smoothly descending frequency over 7 minutes is not the kind of signal you would expect from a brief collision or a sudden fracture. It requires a process that changes gradually and continuously over that duration. One possibility is that the geometry of contact between the ice and the seafloor changes progressively as the iceberg moves, the angle shifts, or the surface area of contact changes, or the specific topographic feature the keel is engaging with alters the resonance characteristics of the interaction. Any of these changes could, in principle, produce a gradual shift in the dominant frequency of the sound being generated. The physics of how ice and rock interact at depth under the pressure and temperature conditions of the deep southern Pacific is complex enough that the precise mechanism has not been confirmed through controlled observation or laboratory experiment. This is the kind of honest limitation that deep ocean acoustic research runs into regularly. The instruments can detect the sound, the triangulation can estimate the location, the frequency profile can be described with precision, but the source region is inaccessible, far from any port, far below the surface, covered by ocean and ice, and the full weight of distance, and so the proposed mechanism remains a hypothesis, a well-supported one, arrived at by researchers who know a great deal about how ice behaves acoustically and what kinds of physical interactions produce sustained, low-frequency acoustic signals, but a hypothesis nonetheless, because no one has been there to watch it happen. What makes slowdown particularly interesting as a research subject is the shape of its uncertainty. The triangulation places it in a plausible region. The frequency range fits the known properties of acoustic propagation through the ocean's deep channel. The proposed mechanism, ice-seafloor interaction, is physically coherent and consistent with what researchers know about how large icebergs behave. The remaining question is not whether the explanation is plausible. It is whether the specific physical geometry that would produce exactly this smooth 7-minute descent can be fully specified and confirmed. And that question has stayed open because slowdown has not been recorded again in its distinctive form since May 19, 1997. A single detection is a particular kind of limitation. It means the researchers have a very precise description of one event, this recording, this spectrogram, these arrival times, and no second example to compare it against. With Upsweep, which returns seasonally, researchers can observe the pattern repeating and look for subtle changes from one year to the next, variations in amplitude or frequency range that might offer clues about the source. With Julia, recorded on a single occasion, researchers at least had the network-wide detection across multiple stations to work with, giving them good triangulation data. Slowdown sits in a similar position to Julia in that sense. One detection, one spectrogram, one set of arrival time measurements, but with the added peculiarity of its uniquely smooth acoustic profile, which has no obvious parallel in the catalog of other sounds the network has recorded. The hydrophone stations that registered it have been running continuously since. The Equatorial Pacific Array monitors the ocean's acoustic environment around the clock, logging signals from earthquakes, volcanic events, passing ships, marine mammals, and the occasional anomalous recording that does not fit into any of those categories. In the years since 1997, the instruments have continued to record the ambient acoustic life of the Pacific Basin in considerable detail. Whatever produced slowdown has not, as far as the recordings show, produced a signal with the same characteristics again, or if it has not been detected. The two conditions are not the same thing. A signal produced in a remote region of the southern Pacific might travel to the equatorial array under conditions that vary with season, with the specific geometry of the SOFAR channel at that time of year, with the acoustic properties of the intervening water mass. Some events happen and are heard, some may happen and are not. There is a quality to slow down as a scientific object that is worth holding for a moment. The name is descriptive in a very plain, accurate way. It describes exactly what the spectrogram shows, a tone slowing down, frequency decreasing, from the beginning of the recording to the end. The researchers who named it were applying the same practical approach they applied to all the anomalous signals they cataloged. Look at the spectrogram, find the most distinctive visual or acoustic feature, and use it as the name. It is a working title that became a permanent one, the way working titles sometimes do when no better alternative arrives. In this case, no better alternative has arrived because the sound has not been heard again, and without a second detection, there is no additional information that would suggest a more specific or more explanatory label. The spectrogram of slow down, when seen alongside the spectrograms of other anomalous sounds recorded by the same network during the same era, stands out for its visual simplicity. Other recordings are more complex, multiple tonal components, irregular frequency variations, rising and falling patterns that suggest intermittent rather than continuous sources. Slow down is just the one line, descending smoothly. In acoustic terms, that simplicity is actually informative. A single sustained tone that changes gradually in frequency suggests a source that is physically coherent over the duration of the event, not multiple sources interacting, not a series of separate events, but one continuous process evolving slowly in one direction. Whatever was happening on May 19th, 1997, in the Southern Pacific, it was happening in an organized, sustained, and gradually changing way for 7 minutes, and then it stopped. The cessation is also interesting. Slow down ends. The descent reaches a lower frequency, and the signal fades from the recording. One possibility is that the process simply concluded. The iceberg moved past the topographic feature it had been engaging with, or the contact ended, or the geometry changed enough that the resonance collapsed. Another possibility is that the signal continued, but fell below the detection threshold of the instruments into a frequency range too low to be registered clearly, or reduced in amplitude to a point where the ambient noise floor obscured it. The recording does not, by itself, distinguish between these possibilities. It shows that the signal was present, and then was not, and that is what the instruments captured. On the day Slowdown was recorded, the Southern Pacific was doing what the Southern Pacific does in May, which is move. The circumpolar current was running eastward at depth. The winds at the surface were variable at best and considerably stronger than variable at worst. This region being one where the atmospheric pressure gradient between the subtropics and the polar south produces sustained westerly winds that sailors have historically named with some feeling the roaring 40s, the furious 50s, the screaming 60s, reflecting the latitudes and the winds that inhabit them. At depth below the weather, the water was cold and dark and very still relative to the turbulence above. The acoustic conditions at so far depth were, as they generally are in this region, well suited for long-range propagation. A signal with the right frequency and enough initial power would have little difficulty traveling northward through the water column toward the equatorial array. The hydrophone stations in the equatorial Pacific are moored at or near so far depth, the horizontal layer of the ocean where sound velocity reaches a minimum and acoustic energy naturally concentrates. At that depth, a signal produced thousands of kilometers away in the southern Pacific would arrive after traveling for hours through the water, its wavefront gradually broadening as it moved, but losing very little energy to absorption, because the frequencies involved are low enough that the seawater's absorptive properties have relatively little effect. By the time Slowdown reached the nearest station in the equatorial array, it had covered an enormous distance. The arrival time differences between stations, those small fractions of a second that the triangulation depends on, Record the geometry of that journey in compressed form, a mathematical trace of where the signal had been. The researchers who worked with slowdown in the late 1990s were operating within a relatively new paradigm for ocean acoustics. The civilian use of the hydrophone network that NOAA had access to, including elements of the former Navy listening infrastructure, had only been available for a few years at that point, and the catalog of anomalous sounds was still being built. Each new unusual recording was treated as a data point in an emerging picture of the ocean's acoustic environment, a picture that turned out to be considerably more active and varied than anyone had fully anticipated. The deep Pacific was not quiet. It was full of sounds, geological, biological, physical, at frequencies that the human ear cannot access without pitch shifting, generated by processes that ranged from the well understood to the genuinely unknown. Slowdown was one of the genuinely unknown ones, and the researchers placed it in the catalog with the same careful descriptive approach they applied to everything else. Record the date, describe the frequency profile, estimate the source location, and note that the source is not confirmed. What the catalog approach produces over time is a kind of patient record keeping that has its own value independent of whether any given sound is ever fully explained. The catalog says, on this date, at this frequency, a signal arrived. It says the source was estimated to be in this region. It says the proposed mechanism is consistent with the data but has not been confirmed. And then it stays open, a file that remains in the database, available for future researchers who might have better tools or better data, or a new hypothesis that connects slowdown to something not yet understood. The file does not close because the explanation has not arrived. It stays open because the ocean is very large and the recording is very specific, and the question is genuinely unresolved. And that combination does not require a resolution in order to be handled with care. The Southern Pacific, in the broad region where slowdown's source was estimated, is not well surveyed by direct physical methods. Research vessels do reach that area. It is remote, but not entirely unknown, and bathymetric data from sonar mapping gives researchers a reasonably detailed picture of the seafloor topography in many parts of the region, including the general character of the Eltanin fracture zone. But detailed, sustained observation of the acoustic environment at depth in the specific area where slowdown likely originated is not something that has been achieved. The hydrophone network provides a passive record, sounds that travel to it from a distance, but cannot tell researchers what was visually or physically happening at the source at the moment of recording. That gap between acoustic detection and physical observation is one of the fundamental constraints of deep ocean science, and slowdown sits squarely within it. There is a particular quality to acoustic data that makes this gap feel a certain way. Sound is invisible. It propagates through a medium that is also invisible from the surface, in a region of the ocean that is entirely dark, at depths where no direct observation is possible without specialized equipment that was not present at the time. What the recording provides is real. The signal arrived. The instruments registered it. The spectrogram is an accurate representation of the acoustic event, but it is a trace, not a view. Researchers work with traces. They work with the shapes that sounds leave in the recording medium, and they build explanations from those shapes by combining them with what is known about the physical processes that could have produced them. In most cases, the trace and the knowledge together are enough to arrive at a confident explanation. In some cases, slow down among them, they are enough to arrive at a plausible explanation that remains short of confirmed. The sound itself, when pitch shifted to a range the human ear can register, has a quality that the spectrogram's clean descending line only partially captures. It begins as a tone, audible, low, sustained, and descends over its full duration in a way that is smooth enough to hear as a continuous change rather than a series of steps. It does not sound mechanical, exactly, though the proposed explanation involves physical contact between ice and rock. It does not sound biological. It sounds in some ways like a very slow exhalation, a sustained note losing frequency over 7 minutes in a manner that is too gradual to track moment by moment, but unmistakable when the beginning and the end are compared. The note that begins the recording and the note that ends it are measurably, audibly different. Everything in between is the transition. 7 minutes is a long time for a single continuous acoustic event in the deep ocean. Earthquakes produce signals that can last many minutes, but they typically involve complex waveforms with multiple phases rather than a single sustained tone. Biological sounds, whale calls for instance, can be long and sustained, but their frequency profiles are generally more complex and more variable than slowdown's clean descent. Volcanic tremor can be sustained for hours or days, but it produces a different spectral signature, typically more broadband and less specifically shaped than a single descending tone. Slowdown sits outside the easy categories. It fits the general character of ice-related acoustic events, but in a way that is distinctive enough that it has not been matched to any other recording in the catalog with a high degree of confidence. For the researchers who work with the acoustic catalog, this distinctiveness is part of what makes the record interesting. The deep ocean produces a range of sounds that science is still characterizing, some well understood, some proposed and plausible, some genuinely open. Slow down occupies the middle category, proposed and plausible, with the additional note that the single detection limits what can be said with confidence. If it were recorded again, in the same region, with the same characteristic descent, researchers would have the opportunity to compare the two events, look for correlations with other data sources, sea ice conditions in the region, iceberg tracking data from the period, seismic records, and potentially build a more specific and confirmable account of the mechanism. One recording is a question. 2 recordings are the beginning of a pattern. Slowdown has stayed, for now at 1. The instruments in the equatorial Pacific that recorded it in 1997 are part of a monitoring program that has continued operating since. The technology has improved in various ways: data storage, transmission, processing, and the understanding of the ocean's acoustic environment has grown considerably in the years since the mid-1990s. Researchers now have access to satellite tracking data for large icebergs in the Southern Ocean, which allows them to correlate acoustic events with known iceberg positions and movements in a way that was not possible in 1997. If a sound like Slowdown were recorded today, researchers would be able to check the iceberg tracking database for large ice bodies in the vicinity of the estimated source region on that date and look for candidates whose position and trajectory were consistent with the kind of ice-seafloor interaction the hypothesis proposes. That correlation would not confirm the mechanism directly. The physics of what happens when a large iceberg's keel contacts irregular seafloor topography is still not fully characterized, but it would significantly constrain the range of possible explanations. That capability did not exist in May of 1997. The researchers who heard Slowdown worked with what they had: the recordings, the triangulation, the growing body of knowledge about ice acoustics, and the physical properties of the Southern Pacific in that region. They produced a reasonable account and placed it in the catalog. The catalog has stayed open since, and the instruments have kept listening, and in the years that have passed, the Southern Pacific has continued to do what it does: move and freeze and calve ice, and carry that ice northward and grind it sometimes against the rough and irregular seafloor that the Elton fracture zone has built over millions of years of tectonic process. Whatever produced Slowdown may have produced it more than once since 1997, in conditions that differed slightly from those of the original recording. Different iceberg, different topographic feature, different acoustic coupling geometry that routed the signal differently or attenuated it more before it reached the equatorial array. The catalog shows no match. That could mean the event has not recurred in a form that reached the instruments. It could mean it has recurred but in a frequency range or power level that placed it below the detection threshold. It could mean the source was a specific combination of ice body, seafloor geometry, and acoustic conditions that simply has not repeated. The instruments cannot distinguish between these possibilities, and the question sits, as it has for more than 2 decades, in the patient and comfortable position of something noted and not yet answered. A sound heard once in a remote stretch of ocean, traveling thousands of kilometers to arrive at an instrument it was never aimed at, producing a spectrogram whose clean descending line still prompts a pause when researchers encounter it for the first time. That is what Slowdown is. The line on the screen is precise and real. The instruments that recorded it have continued to listen in the years since, registering the acoustic texture of the equatorial Pacific, day after day and year after year, the rumble of distant shipping, the long calls of whales passing through the corridor, the T-phase arrivals of earthquakes from the Pacific's seismically active margins, and beneath all of it, the low and continuous murmur of the ocean's own physical processes, the geological background noise of a planet whose interior has not finished moving. Against all of that, Slowdown appeared once, descended smoothly for 7 minutes, and ended. The instruments recorded it. The record has been kept. Somewhere in the southern Pacific, in the cold and irregular terrain of the seafloor near the Alton fracture zone. The conditions that produced it may or may not exist tonight in some form. Ice drifting north, a keel approaching contact, a frequency about to begin its long, slow, smooth descent through the water toward instruments that have been waiting, without impatience, for more than 27 years. The recording from 1997 sits in the database alongside everything else the network has heard. It has not been matched. It has not been closed. It remains exactly what it was when the researchers first saw its shape on the spectrogram, a line descending, clean and deliberate looking, across 7 minutes of a morning in May, still waiting for the second listening that would let someone understand it more fully. The instruments in the dark water continuing to record, continuing to wait, in the particular and comfortable way that scientific attention waits, open, unhurried, and not at all troubled by the quiet. At 400 atmospheres of pressure, a cubic meter of seawater becomes something that is difficult to hold in the mind all at once. The pressure is not a force pressing inward from one direction. It arrives from every surface simultaneously, equal and complete, the way cold arrives when the temperature drops past a certain point, and there is nowhere in the room that is warmer than anywhere else. The water temperature down here sits near 2 degrees Celsius, which is close to freezing without being frozen, held liquid by the salt dissolved through every part of it. There is no light. There has not been light at this depth for as long as this water has been at this depth, which is a very long time, and the darkness is not the darkness of a room with the curtains closed or a road with no streetlights. It is the darkness of a place that light has simply never reached, a condition of the environment rather than an absence of something that was once present. This is the abyssal zone, the deep floor of the world's largest ocean, and it is not empty. the pressure that would collapse most familiar structures. A car compresses to roughly the size of a football at these depths is the same pressure that has shaped over millions of years the organisms that live here. Their cells work differently, their proteins fold differently. The biochemical machinery that keeps them running has been refined through geological time to function at conditions that would disrupt the same machinery in any creature from a shallower world. This is not an extreme environment for them, it is simply the environment. A deep-sea dragonfish moving slowly through the water column at 1,500 meters does not experience the pressure as pressure. It experiences it as the world, which is what it is. The darkness at these depths is not uniform in the way that darkness at the surface might seem uniform on a moonless night. Down here, the darkness generates its own interruptions along the flanks of underwater ridges, in the open water of the deep column, and along the soft sediment of the abyssal plain. Bioluminescence persists as a low, intermittent, and widely distributed phenomenon, not a continuous glow, but a scattered and irregular light produced by living things as a byproduct of chemistry. A siphonophore drifts through the water here, a colonial organism formed from dozens of specialized individual bodies linked into a single long chain, some members of the chain dedicated to movement, some to feeding, some to reproduction, and some producing a faint blue-green chemical light that pulsed very gently as the animal moved. The light is not warm, it illuminates almost nothing. To any instrument that could measure it, the energy involved would be negligible. But it is there, in the dark, a small persistent fact about what this place contains. A siphonophore of this kind can reach lengths of several meters, making it among the longest animals in the ocean by some measures, though length in this case is not the same thing as size in any intuitive sense. The organism is more like a living thread than a living body, extremely long and extremely thin, drifting with the current and extending its stinging tentacles outward into the surrounding water to intercept small prey. It has no brain. It has no single center of experience, if experience is even a useful frame for what a siphonophore has. The individual bodies that make it up are genetically identical, each grown from the same original larva that settled into a colonial configuration rather than a solitary one, and the division of labor among them is almost architectural, each unit doing one thing, the whole assembly doing something none of the parts could accomplish alone. In the darkness around it, things are happening at scales the animal cannot detect and would not respond to if it could. A low-frequency sound wave is passing through the water, generated far to the south, traveling northward through the ocean at roughly 1,500 meters per second. Sound moves well through water, and it moves considerably faster than it moves through air, and it moves through seawater better than it moves through fresh water because the salt adds density, and the density changes the acoustic properties of the medium in ways that allow vibrations to propagate with less energy lost over distance. This general principle that sound propagates well through water is a starting point, but the actual acoustic behavior of the ocean is more specific and more particular than the general principle suggests. The ocean is not a uniform medium. Temperature, pressure, and salinity all affect the speed at which sound travels, and because these properties vary with depth, the speed of sound varies with depth, and that variation has a structural consequence that turns out to be one of the most acoustically important features of the ocean anywhere on Earth. In the open Pacific, at roughly 600 to 1,200 meters below the surface, the speed of sound passes through a local minimum. Above this depth, water temperature is falling as depth increases, and falling temperature slows sound, so sound moves more slowly as depth increases toward this layer. Below this depth, temperature changes much less, but pressure increases with depth, and increasing pressure speeds sound up, so sound moves faster as depth increases below this layer. The result is a zone, a horizontal corridor running through the ocean at intermediate depth, where sound traveling at any angle gets bent by refraction back toward the axis of the corridor. A low-frequency sound wave that enters this layer finds itself continuously redirected back toward the zone's center, guided horizontally through the ocean rather than spreading outward in all directions. The energy stays concentrated. The signal remains detectable. A sound that enters this layer in one part of the Pacific can travel for thousands of kilometers and arrive at the far side of the basin, still carrying enough energy to register on a sensitive instrument. This corridor is sometimes called the SOFAR channel, which stands for sound fixing and ranging, a name applied to it when its acoustic properties were first formally documented in the mid-20th century. The name was chosen for practical rather than poetic reasons. The channel was of immediate interest because it could carry acoustic signals across ocean basins, and the practical applications of that property were apparent to anyone paying attention at the time. But the name has a certain accidental rightness to it anyway, because the channel does fix sounds in a range, holds them within a horizontal band of ocean, keeps them propagating rather than dispersing, guides them across the water in a way that nothing in the atmosphere quite matches at comparable distances. The SOFAR channel's central axis in the open Pacific sits at roughly 800 meters below the surface, in water that is cold, dark, and under considerable pressure. A hydrophone instrument placed at this depth, moored to the seafloor by a long cable and held at depth by a combination of buoyancy and anchoring, sits in the channel's approximate center and receives acoustic energy arriving from every direction along the channel's axis, from the north and south, from the east and west, from volcanic ridges and distant ships and blue whales calling thousands of kilometers away. The instrument does not know where any of these sounds came from. It registers pressure variations in the water around it and converts those variations into electrical signals, which are stored or transmitted for later analysis. The instrument is patient in the way that instruments are patient, which is to say that it is indifferent to time and registers what passes through it without preference or boredom. In a single 24-hour period, an instrument like this might record several dozen distinct acoustic events. A large cargo vessel moving at 12 to 15 knots through the North Pacific produces a broadband mechanical noise from its propellers and engine that propagates down into the SOFAR channel and travels southward for hours. The noise arrives at the hydrophone as a gradual rise in the low-frequency ambient level, a slow increase in acoustic energy across a range of frequencies that climbs as the ship approaches and then falls as the ship passes and continues moving away. The shape of that passage, the rise and fall of energy over time, carries information about the ship's bearing and speed, and a researcher who has spent years looking at spectrograms can read a ship's passage the way a person who has lived near a road for a long time can tell from the sound whether a passing vehicle is a small car or a heavy truck, and roughly how fast it is moving. After the ship's signature fades, there is a period of relative quiet. The ambient noise floor of the deep Pacific, in a region away from major shipping lanes, is low, lower than most people would expect if they had not studied it. And in that quiet period, the hydrophone records the ocean's own internal acoustic life. Somewhere to the southwest of the instrument, a group of fin whales is moving. The fin whale is among the largest animals alive, and among the loudest. It produces low-frequency calls at around 20 hertz that propagate efficiently through the SOFAR channel and can be detected hundreds of kilometers from the calling animal. The calls come in long sequences, each call a sustained, low, downward sweeping tone that lasts about 1 second, repeated at roughly regular intervals that can go on for hours. On a spectrogram, a sequence of fin whale calls looks like a series of short downward strokes, evenly spaced, moving from left to right across the display. The instrument records them without emphasis, the same way it records the cargo ship and the geological murmur rising from the seafloor and the long quiet intervals between a small tectonic event along the Aleutian Arc, thousands of kilometers to the north, generates a T phase, a seismic wave that has converted from traveling through rock into traveling through water at the seafloor boundary, and now propagates southward through the SOFAR channel as an acoustic signal. T phases from distant earthquakes arrive at equatorial Pacific hydrophones as a low emergent roar that builds slowly, peaks, and then fades over the course of several minutes, a sound with a particular shape on a spectrogram that experienced researchers distinguish from biological and ship noise without much difficulty. The earthquake that generated this T phase was not large enough to cause damage anywhere. It was the kind of small event that the Earth produces continuously along its active plate boundaries, a small release in a system that is always somewhere adjusting. The T phase that it sent into the SOF channel has been traveling for about 40 minutes by the time it reaches the hydrophone, carrying information about the seismic event across the width of the northern Pacific in the form of compressed and rarefied water. The deep ocean is, among many other things, a geological instrument. The seafloor is not a static surface. Along the underwater ridges that run through the Pacific Basin, new oceanic crust is being formed continuously by the upwelling of basaltic magma through long fissures in the rock. The East Pacific Rise, one of the major spreading centers in the Pacific, adds new seafloor at a rate of several centimeters per year, fast in geological terms, which means the East Pacific Rise is among the more active spreading centers on Earth. The process is not smooth. Magma moving through conduits in the rock, fluids superheated by proximity to magma and moving under pressure through hydrothermal systems, the slow fracturing of cooling rock as it moves away from the spreading center and contracts. All of these processes generate acoustic energy in the low frequency range, energy that couples into the surrounding seawater and enters the SOFAR channel and propagates outward. The deep ocean is, at its floor, continuously vibrating at frequencies too low for human hearing to resolve, and has been doing so for as long as there have been active spreading ridges in the Pacific, which is a very long time. Below the spreading ridges, below the hydrothermal vent fields, where superheated water exits the seafloor in columns of dark mineral-rich fluid, below the abyssal plains where sediment accumulates at a rate of millimeters per 1,000 years. The crust thickens as it cools and moves slowly toward the subduction zones, where it will eventually descend back into the mantle. The oldest seafloor in the Pacific is near the western margins, moving toward the trenches where the plate descends, rock that was formed at a spreading center tens of millions of years ago and has been traveling slowly across the basin ever since, cooling and subsiding and accumulating sediment the entire way. The age of the ocean floor is written in its depth, its density, and the thickness of the sediment on top of it, and all of it is moving, all of it is part of a system that has been in continuous motion since long before the Pacific Ocean took its present form. The creatures living in the deep water above this floor have no experience of geological time. An anglerfish at 1,500 meters depth lives on timescales of years, moving slowly through the dark water, using the bioluminescent lure that extends from a modified dorsal fin above its head to attract prey. The lure produces light through a symbiotic relationship with bioluminescent bacteria that live within the lure tissue. The anglerfish provides the bacteria with a stable environment, and the bacteria produce the light that the anglerfish uses to hunt. The light is cold, small, and very local. It illuminates a small sphere of water in front of the fish and nothing else. The anglerfish cannot see past the edge of that sphere. It waits, drifting, for something to come within range of the light, and when something does, it acts. The deep Pacific is not a simple biological desert, despite the conditions that might suggest one. Below 1,000 meters, in the permanently dark zone called the aphotic zone, named for the absence of light available for photosynthesis, the ocean still supports a complex web of organisms. Many of them depend indirectly on the productivity of the surface ocean above them, feeding on particles of organic material that sink slowly from the upper water column as marine snow, a continuous gentle rain of dead organisms, fecal material, and organic aggregates drifting downward through the water column over days and weeks. By the time this material reaches abyssal depth, most of it has been consumed or decomposed, but enough reaches the bottom to support a community of organisms on and just above the seafloor, sea cucumbers moving slowly across the sediment, small crustaceans, bacterial mats around hydrothermal features. The total weight of living material in the deep ocean is small compared to the surface, but the deep ocean's total volume is enormous, and the organisms within it are real and present and going about their lives in the same continuous way that organisms everywhere are going about their lives. The aphotic zone begins at roughly 200 meters depth and extends to the seafloor, wherever the seafloor is. Below 200 meters, there is not enough light for photosynthesis. The sunlight that reaches the ocean's surface is absorbed and scattered by the water above, and by 200 meters depth, even on the brightest days, the light that remains is too faint and too altered in its spectrum to support the biochemical reactions that plants and phytoplankton use to fix energy from sunlight. Below 600 or 700 meters, there is no light at all under any circumstances. Not even the faintest trace of surface light penetrates this far. The aphotic zone encompasses, by volume, the vast majority of all ocean water on Earth. Most of the ocean, measured by volume, is dark and cold and under considerable pressure. The well-lit, productive surface layer, the part of the ocean most familiar from human experience, the part visible from a boat or a beach, represents a thin skin at the top of a very deep system. Acoustic methods have become central to the scientific study of this dark and largely inaccessible volume for a straightforward reason. Sound propagates through it where light cannot. A sonar pulse sent downward from a ship can map the seafloor. It would take years of direct sampling to characterize. A passive hydrophone at so far depth can detect the acoustic signatures of whale populations, tectonic events, and volcanic activity across an area that no direct survey could cover in real time. The physical inaccessibility of the deep ocean, the cost and difficulty of getting instruments to the sea floor, the pressure and temperature conditions that damage conventional equipment, the vast distances involved, has made passive acoustic monitoring one of the most productive scientific tools available for understanding what happens in these depths. The instruments sit at depth and listen, and what they hear builds, over years and decades, into a picture of the ocean's acoustic life that no other method could produce. That picture includes things that were expected and things that were not. It includes the regular acoustic signatures of known geological processes, seafloor spreading, tectonic events, hydrothermal activity, arriving with the predictability of physical systems operating according to understood principles. It includes the acoustic signatures of biological populations, the calls of large whales, the sounds of aggregated fish and shrimp, the occasional brief, unusual signal from something that moved through the area and left its sound behind. It includes the passage of ships, the distant rumble of distant storms generating surface waves, the low ambient hiss of the ocean's own thermal and hydrodynamic processes. And it includes, in the archive that has accumulated over decades of continuous monitoring, a number of recordings that do not fit cleanly into any of these categories. Signals that arrived, were recorded, and remain in the record as honest entries in a catalog of things that have been heard and not yet fully explained. The scientific response to these unexplained recordings has been methodical and patient. Researchers compare the signals to the known acoustic signatures of geological and biological processes, looking for matches or near matches that might point toward an explanation. They use the arrival times of a signal at multiple geographically separated instruments to triangulate its probable source region. They look for contextual information, records of seismic events in the relevant region on the relevant day, reports of unusual oceanographic conditions, historical records of ice conditions in high-latitude areas near the probable source. The process is not quick. Some signals yield to explanation over the course of months, others take years. A few have been in the catalog for decades without a definitive resolution that satisfies everyone who has examined them. The appropriate response to this, in scientific terms, is to keep the records, maintain the instruments, and remain open to new data. An instrument moored at so far depth in the equatorial Pacific has been running continuously, or nearly continuously, for decades in some cases. It has recorded the ocean through periods of high volcanic activity along the Pacific spreading centers and periods of relative quiet. It has recorded the passage of seasonal changes in the ship traffic patterns above it, the seasonal variations in whale calling behavior, the gradual long-term shifts in ocean temperature that are slowly changing the acoustic properties of the water the signals travel through. It sits at depth, in the dark, under pressure, in water near 2 degrees Celsius, and it listens with the specific patient quality of a physical instrument that has no experience of time, that makes no distinction between the first day it was deployed and the 10,000th, that registers what passes through it and records it without emphasis or preference. Along the East Pacific Rise, at this moment, magma is moving through conduits in the rock that it has carved and recarved over millions of years. The movement is slow by human standards, slow enough that the seafloor above the spreading center is essentially stable from one year to the next, but not so slow that it is acoustically silent. Fluid moving under pressure through narrow rock passages generates a particular kind of low-frequency vibration, a sustained tremor that is distinct from the sharp impulsive signal of a fracture event or an earthquake. The tremor propagates outward through the rock and couples into the water at the seafloor boundary, and from there it enters the water column and travels upward toward the SOF channel. By the time it reaches the channel's axis, the signal has spread and weakened, but at low frequencies the ocean is a very efficient medium, and what remains is still detectable at considerable distance. A hydrophone, 1,000 kilometers from the East Pacific Rise, picks up this geological background as a low, broad, continuous feature in the acoustic record, part of what oceanographers mean when they talk about the ocean's ambient noise floor. The low background level of sound that exists in the deep ocean even when nothing unusual is happening. The ocean's ambient noise floor has been studied formally since the mid 20th century, and it has been found to be both consistent in its general structure and variable in its details. Its dominant contributors shift depending on frequency range. At the lowest frequencies, geological activity and distant shipping dominate. In the middle, low frequency range, wind generated surface waves and shipping contribute roughly equally. At higher frequencies, thermal noise and biological sources become more prominent. The overall level of this ambient noise has increased somewhat since the mid 20th century, largely due to increased shipping traffic, and the increase has been studied in the context of its potential effects on marine mammals whose communication signals overlap in frequency with the noise sources that have grown louder. The acoustic environment of the deep ocean is not static. It changes with the seasons, with human activity, and with long-term shifts in oceanic and atmospheric conditions, and the instruments that have been monitoring it long enough have recorded those changes in their archives alongside the anomalous signals and the whale calls and the geological events. What all of this amounts to, the instruments, the archives, the decades of accumulated recordings, the patient scientific work of triangulating and cataloging and comparing, is a sustained act of listening. The deep ocean is not a place that was designed to be listened to. It is a place that turned out to be full of sound once the instruments existed to hear it, and the sounds that have emerged from it over the decades of formal monitoring include some of the most unusual acoustic recordings made anywhere on Earth. They include sounds that match the known signatures of geological processes, sounds that match the known signatures of biological populations, and sounds that resist easy classification and remain in the catalog under the informal descriptive names that researchers gave them when they first encountered the signals and needed something to write in the logbook. The act of naming an unclassified sound, giving it a short descriptive label based on its visual appearance on a spectrogram or its acoustic character when pitch shifted into audible range, is a practical measure in the first instance, something to write in the logbook and use in conversation with colleagues. But the names accumulate over time and form something that functions a little like a natural history, a list of things encountered in a particular environment that have been noted and recorded and given the dignity of a name, even when their full identity remains unknown. The names are not claims about origin or significance. They are placeholders in a process that continues, markers for signals that entered the record and remain there, waiting for the additional data or the new analytical framework that might eventually place them in a larger context. The water through which all of this acoustic activity moves is in slow and constant motion. The thermohaline circulation, driven by differences in water temperature and salinity across the global ocean, moves water masses through the deep Pacific over timescales of centuries. The deep water now occupying the abyssal Pacific may have been at the surface in the North Atlantic or around Antarctica hundreds or thousands of years ago, and will not see the surface again for centuries. As this water moves slowly through the deep basin, it carries with it whatever dissolved gases and minerals it acquired at the surface, along with the chemical memory of its origins, written in its temperature, salinity, and isotopic composition. It is old water, in a meaningful sense, water that has been away from the light for a very long time. Within this old, slow, cold water, the acoustic signals that the ocean generates continue to travel. To know, a low-frequency tone originating at a volcanic vent on the Pacific Antarctic Ridge moves northward through the SOFAR channel, refracted continuously back toward the channel's axis by the pressure gradient below and the temperature gradient above. It has been traveling for more than an hour. The signal has weakened as it has spread, but the SOFAR channel's guiding effect has kept it from dispersing as quickly as it would in a homogeneous medium. The acoustic energy is still concentrated within the channel's bounds, still propagating as a coherent signal rather than a diffuse wash of noise. The water around it is dark and cold. The pressure on every surface is equal and complete. A siphonophore drifts slowly through the water column several hundred meters above the signal's path, producing its faint blue-green light in pulses that illuminate nothing, and the signal passes through the water below it without any interaction that either the organism or the signal would register. The signal will reach the nearest hydrophone station in about another hour. When it arrives, the instrument's pressure-sensitive transducer will register it as a small change in the electrical signal it is continuously generating, a deflection in the record, brief and specific in its frequency character, arriving out of the ambient noise floor and then returning to it. The instrument will record this deflection along with everything else it recorded in the same period: the background geological murmur, the passage of water currents across its casing, the distant signature of a ship somewhere far to the north. A researcher reviewing the archive later may notice the signal, or may not, depending on what they are looking for and how the automated detection systems are configured. If it is noticed, it will be logged. If it is distinctive enough, it will be named, or compared to existing entries in the catalog, or flagged for further analysis. If it looks like something already known, it will be filed accordingly. If it does not, it will be held open. This is how ocean science at these depths has always worked, patiently, with instruments moored in places that no person will visit, recording what passes through them, accumulating an archive that grows one day at a time and reveals its contents gradually, over years, to the people who study it. The deep Pacific is too large and too inaccessible for any other approach. The basin spans more than 15,000 kilometers at its widest, from the continental margins of Asia to the coasts of North and South America, and from the Arctic margins in the north to the Antarctic waters in the south. Its average depth is more than 4,000 meters. Its total water volume is larger than all the dry land on Earth, measured in cubic kilometers. No ship-based survey could cover it in any continuous sense, and the seafloor and deep water column remain, outside the small areas that have been directly sampled or remotely observed, among the least well-characterized environments on the planet. The hydrophone networks that sit within this volume are a small set of instruments distributed across an enormous space, and what they record is a sample, a partial and geographically limited sample, of the acoustic activity happening across the whole basin at any given moment. The signals that have made it into the formal record, the unusual ones that earned names and dedicated analysis, arrived at instruments that were in the right place to hear them. Other signals of unknown character and unknown origin almost certainly passed through parts of the basin where no instrument was positioned to receive them, and entered and exited the SOFAR channel unheard by any human device. The catalog is what the instruments captured. The ocean is larger than the catalog. At this moment, the low-frequency signal continues northward through the SOFAR channel, in water near 2 degrees Celsius, in total and permanent darkness, at roughly 1,500 meters per second. The water it moves through has been at this depth for longer than any person has been alive. The seafloor below it has been forming and moving for tens of millions of years. Above it, on the ocean's surface, there is daylight somewhere and darkness somewhere else, and ships are crossing the open Pacific, and weather systems are building and dissipating, and none of this reaches the signal or the cold water the signal is moving through. Down here, things are very still except for the sound, and the sound is traveling north, carrying whatever information it holds about where it came from, moving through the dark at a steady and unhurried pace, as patient as the instruments that will eventually, in another hour, register its arrival. The instrument at the far end is already listening. It has been listening since it was deployed, which was many years ago now, and it will keep listening after the signal arrives, and after the signal has passed through, and after the archive has grown another small increment from this night's recording.